Let's get into the stereochemistry of compounds that have two chiral centers and also some cyclic structures now. So when you have more than one chiral center, what does that mean for the number of enantiomers? So the first thing is each chiral center is going to have a set of enantiomers, right? A pair, two enantiomers. So which means that if you have more than one chiral center, if you have two chiral centers, then you have two enantiomers for each of those chiral centers, right? So which means that anything with two chiral centers will have four enantiomers, but not all four of them are mirror images of each other, right? Because enantiomers are only two. You can only have two mirror images, okay? One the original and one for the mirror. So which means the other two are something different, okay? Which is why we're talking about this. Well, that was for two chiral centers. What if you have more chiral centers? Then how do you determine how many isomers you're going to have? And that is given by this formula, 2 to the power of n, where n is the number of chiral centers. So that way you don't have to, sit down and think, okay, how many chiral centers, this is an easier calculation. That's all I'm saying. All right. So any stereoisomer that has 4 chiral centers will have 16 stereoisomers. Okay, so that's a lot. And this is something that happens in carbohydrate chemistry, for example, which has, a glucose molecule will have 4 chiral centers. So the family is so big just because there are so many isomers in there. Okay, so that it's kind of a normal thing to have, and it can be a problem in the sense that some of those isomers are useful, some of them are not, some of them are good, some of them are not, so on and so forth. So anyway, so that is the number of isomers. So here I've just given you some examples that you can have chiral centers. So here I have given you chiral centers that are all different. Here you can see there is some symmetry, but each of the chiral center is still a chiral center. Then here you have two chiral centers, but you can see that there's like some symmetry in there, which we'll talk about. That's why I've kind of given this here. And then again, you'll have something typical as in the last compound, which is also cyclic and then has 3 chiral centers in it. Okay, so let's continue on. All right, so here is a molecule with 2 chiral centers. So again, 2 chiral centers means that you'll have 4 stereoisomers. Okay, so you can read all of this or you can just listen to me for now. So look at this compound over here. All right, so you have a CH3, you have a C2H5 here. 1, 2, 3, 4, 5. This is a 5 carbon structure which has 2 bromines on it. Okay, and these 2 bromines, because of their location, you have 2 chiral centers, okay, on here. So the mirror image for this compound is going to be this, right, where the bromine and the bromine is on the opposite side here. That's how it is. So we'll call this one pair of compound 1, compound 2, and these are enantiomers. Now what happens is look at this compound, this pair of compounds, and you can just look at the third one. Okay, for to begin with. So you still have the CH3, you still have the C2H5, and you still have that 5 carbon compound, right? Remember, we have 2 chiral centers. So if you look here on the top for compound number 1, I have left that as the same, but now we've switched out the bottom one. Now remember the CH3 and the ethyl group here, the C2H5, that has not moved, right? That is still going to the back, this is still going to the back. So which means the only thing I have switched out is Br and H. The only way I can go from compound number 1 to compound number 3 is by breaking a bond. Okay, I have to literally break a bond between Br and then H over here with the carbon and then switch things around. Okay, so that's what I have to do in order to go from 1 to 3. So I want you to understand that compound number 1 and 3 are not just rotations. Okay, they are literally a different orientation. Okay, I should say a 3D orientation. So the bond has been broken. And then here you have the mirror image. Okay, so which means compound number 1 and 3, they are the same in the sense that you still have the 2 bromines on the second and the third carbon. You still have the bromine on the second and the third carbon in structure number 3, but they're not really the same because the bromine has been switched around. Okay, so which means that this compound number 3 and compound number 1, if they are not the same, then what is the relationship? Because the name would be the same. Okay, remember, as we talked about before, with enantiomers, the name is always the same. It's just that R and S is different because the orientation of the molecule, remember, connectivity, that's the most important thing, right? So the connectivity is different. So because of that, these are different compounds. Okay, but they're the same compounds. So we call them different stereoisomers. So if they're different stereoisomers, what is the relationship? We give it a special name, and that's called diastereomers. Okay, so diastereomers are actually stereoisomers that are not mirror images of each other. 1 and 2 are mirror images, so those are enantiomers. 3 and 4 are enantiomers, but 1 and 3 are diastereomers, 2 and 3 are diastereomers, 2 and 4 are diastereomers, 1 and 4 are diastereomers. Okay, so you can see that's kind of how it works. So which means when we're talking about diastereomers, we're talking about the same compound, except that one chiral carbon has been changed, okay, a little bit, because it's not the mirror image anymore. Okay, that's how two chiral centers work. So just a little bit more, okay, about two chiral centers that we need to talk about. Number one, when we said that enantiomers have same properties, that is still valid. Okay, so whether you have two chiral centers or four chiral centers, within those enantiomers, they will still have the same properties except for the optical rotation, which is in the equal and opposite direction. Okay, so enantiomers still have the same physical properties, everything is the same except for optical rotation. However, diastereomers have no optical relationship. Okay, so in the previous slide, compound number 1 and 3, they have no optical relationship, which means compound 1 could be plus 30 and compound number 3 could be minus 25. Okay, for all we know. So they have no optical relationship. Okay, so which means different rotations. But the biggest difference between diastereomers is that they have different physical properties, okay, which is a big deal because enantiomers have the same physical properties, which makes it really, really hard to study them because you have to first separate them, right? And how do you separate something that is just a teeny bit different? Just the orientation of one atom, okay, makes a big difference. So, but now here with the diastereomers, you can have different physical properties, which means you can separate out the diastereomers, you can study them, okay? Now, diastereomers, within that, you will still have the enantiomers, right? Okay. Then, we need to understand the concept of symmetry. So I have talked about it just a little bit when we were assigning chirality in the beginning, all right? But we're going to deal with a little bit more because now if you have 2 or 3 chiral centers, when you have cyclic compounds, then anything is possible, okay, in there. So we need to understand the importance of symmetry, which then is going to lead to superimposition of molecules. Because if something is symmetric, then it can either fold on each other or it will completely superimpose on each other. And when it does that, it will not have any optical activity, okay? Because again, optical activity is because when you the mirror images do not superimpose on each other. Okay, one last word that I want to clarify, okay, for us. Now, this is a little bit of an issue with me, but you know, I think this is a me issue. A lot of the books and a lot of times you will hear something about, you know, some compounds being achiral, okay? Achiral for me just kind of means that you have no optical center, okay? So you have no chiral center in there, achiral, no chiral center. But actually what achiral means is no optical activity in chemistry, okay? So which means you can still have a chiral center, all right? So achiral means there is no optical activity, but you can still have a chiral center. Okay, so I try not to use this word for, you know, because I don't use this word so much. Okay, so when I say something is achiral, you know, I do mean the no optical activity because I don't want to confuse you. Okay, so what I do is I try to use this word a little bit less because for me achiral means no chiral center, but that's not what we're talking about. Okay, so in chemistry the meaning is for achiral no optical activity, and you'll see what we mean by this, okay, as we go on. So Please remember these few points as we're going along. Okay, so now I'm going to look at a different kind of compound. I showed you a different compound to show you what diastereomers are. Now we're going to look at something a little bit different, okay, here. So this one we're looking at a bromobutane, okay, dibromobutane, and hopefully the nomenclature is not too confusing because, you know, bromo stands for bromine and di stands for 2 bromines. So here we have 4 carbon structure and then we have the 2 bromines. I did the same thing. It's almost a similar molecule as in the one that I showed you before, except here I have a CH3 instead of C2H5, which means this is 4 carbons. The other one was 5 carbons that I had in the previous slides. So here we're dealing with a butane. Okay, so this one here, no problem, right? You can see the BR is on the right and the mirror image BR is on the left, and then so on here as well. So these two are enantiomers, right? So 1 and 2 are enantiomers. Now I did the same thing as I did before, which means that I took from compound number 1, I switched out the BR and H, and I switched out the BR and H, right? So now the BR is on the right hand side. So which means both of the BR are on the right hand side. Now I could have done it for the top also. I can't do both, because I mean, you know, that will give me this compound back. So I could have switched just the top one also, okay, and it will give me this, all right, if I had switched out the top BR and put it on the left. So I just switched out the bottom one. It doesn't really matter, okay. So here we have BR on the right hand side, and here is the mirror image of this compound, okay. So here are the 4 stereoisomers, because remember we have 2 chiral centers, so we have one set of enantiomers and then we have another set of enantiomers. So which means compound number 1 and 3, as we've talked about before, are diastereomers, all right. 1 and 2 are enantiomers, 3 and 4 are enantiomers. But here is what happens. Compound number 3 and 4, the mirror images, which means the enantiomers here, are completely superimposable, okay? And because they are superimposable, they don't have any optical activity, okay? So there are 2 ways to look at it, okay. One is that you can go ahead and take this mirror image out and you can superimpose it, okay, for which you can see the video that I have for you. I think the link is given at the bottom. So and in the slide, next slide, I encourage you to look at the video, but do look at the video, okay. So I show you all of this in that video. But anyhow, the other way to look at this, so one is superimposition, right? You take the mirror image and superimpose on the first one, on the original one. The other way to look at this is by drawing a line of symmetry, okay, over here. So this symmetry line, which is the plane of symmetry, if you look at this and you take this top part of the molecule and fold it like a paper, okay, on top of this, each of the atom will fall on each other, right? Hydrogen on hydrogen, Br on Br, so on. So which means that there is an internal plane of symmetry. When you have internal planes of symmetry, those kind of molecules are considered to be achiral, which means they are not optically active. They still have a chiral center. This is still a chiral center. This is still a chiral center. You still have a RNS, but now you don't have any optical activity. Okay, these kind of compounds are called meso. So when you have enantiomers that completely superimpose on each other, those compounds are called meso. So what's going on right now? Relationship between 1 and 2 enantiomers, 3 and 4 enantiomers, 1 and 3 diastereomers, 3 and 4 meso. So 3 and 4 are enantiomers as well as meso. Okay, so new words. Okay, so a little bit about the meso compounds then, okay? So here I've told you about the videos, okay? So you should see the video so you don't feel like I am messing with your heads, okay? Saying that it will superimpose. It will superimpose. Okay, so these are the set again, okay? For all the enantiomers that I gave you before, or the stereoisomers that I gave you before. So one of the things that I wanted to mention over here for you is that, you know, there is generally a question like, you know, you have 2 chiral centers, here's a molecule, you know, and that has 2 chiral centers. How many stereoisomers can you expect, okay, from that? And so you do your 2 to the power n rule and then you calculate it, okay? However, in something like this, okay, where you have a molecule like this, where you have internal symmetry going on, you don't have 4 stereoisomers. You actually only have 3 stereoisomers. So this is something you have to be careful of. Okay, so is it always going to be the case that when you have two chiral centers that you will have a meso? No, of course not. Okay, because I've talked about the two chiral centers before, right, in one of the previous slides, and that had the ethyl group at the bottom, right? It was a 5-carbon. There was no meso in that one. Even though the Br were on the same side, you could not superimpose it because of that ethyl group. Okay, the other time you can't superimpose is when the Br groups are not the same, okay, or you have different groups. So for example, if one of this was bromine and the other one was chlorine, no way, you can't superimpose those. Okay, that's not going to work. The only reason 3 and 4 is working as a meso is because of internal symmetry. The only reason you have internal symmetry is because you have similar atoms, okay, or groups in there. So it's not always going to be the place that, you know, if you have two chiral centers that you're going to have meso compounds. No, not always. Okay, so make sure you look at the groups that you have on there. What kind of molecule do you have? Do you have symmetry in there? So now if you're asked, you know, how many stereoisomers will form from this compound, you know, just draw the compound and see if it's possible to have some kind of symmetry in there. Okay, don't take anything for granted. For naming the compounds, okay, so again, you're not naming the whole compound. All you're naming is the RNS, okay? That's all you're assigning is RNS configurations. So you follow the same kind of rules, okay, that I've, you know, covered before with you with the RNS, which is that, you know, go ahead and identify the atom, okay, and then assign priorities according to the atom and or atomic number of the atom. And then when you assign priorities, remember you go from the highest to the lowest, A, B, C, and D, of course, which is the lowest priority, you keep it at the back, okay? And then just see if the priority assignment is clockwise or anti-clockwise. So R and S, okay? Clockwise is R. Now, here is what happens with two chiral centers, okay? With two chiral centers, you're going to have to look things a little bit different, okay? Because when you draw something like this, okay, which is a very common way of drawing it, this is what I drew for you before, right? So if you look at the previous slides, you will see that I have something like this also for you. But this is a very common way of drawing out two chiral centers, okay? And that is called a Fisher projection. So we've done Fisher projections before in alkanes, but not so popular, right? In alkanes, we did more of the Newman projection. But here, Fisher projections become really important because they're very easy to write. But the thing is, if you have a Fisher projection, then how do you convert it to a 3D? So I've shown that on the next slide also, but here I will explain that to you really quick as well, is that the groups on the top and the bottom, they're going to the back, and everything going on the horizontal is coming out at you, okay? And the carbon-carbon bond is in the plane. All right, this is when you have two chiral centers. All right, that's when you're looking at two carbons. Then this is going to be the 3D orientation, okay, of a molecule. Now, to figure out the RNS configuration, so I have, you know, of course, the video also is there for you to determine the RNS, but I also have pen cast for you. And remember, my pen casts are all on paper, so they are on 2D, because if you don't have a model set, then you should be able to do this on paper. Okay, and so look at that pen cast also to help you understand, because, you know, there are more examples in there. So there are two ways again of doing chirality, as I said before also, okay, when we were doing the single chiral center, is you either look at the molecule keeping the hydrogen at the back, or you just go ahead and, you know, rotate in such a way that hydrogen goes to the back. Okay, that's all you can do. So there's two things, okay, which is either change your point of view or you rotate the you know, carbon center to make hydrogen go to the back. So it's entirely up to you how you want to do it. What I do generally is I look from the side where the hydrogen is at the back then, okay? The only thing again you have to remember is that the CH3 is going to the back, Br is coming out at you, okay? So when you do the RNS configuration, you know, don't think that CH3 is on the top and then there is Br and then this is it. No, 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 no. Br is coming at you, okay? It's coming out of the plane. It's coming out of your computer screen, okay, at you. So don't forget that. So when you look at it from this side and, you know, CH3 is at the back, I've given you what the orientation would look like. Okay, if you were looking at it from this point of view, this is what it would look like, okay, for you. So, the 3D orientations, can take a little time to get used to. So that's why I always urge you to get a tetrahedral carbon, and that's all you need with 4 groups and 4 colors on it. And that will really help you visualize. Initially, maybe later on you may not need it, okay, but initially it will. So here are the priority groups and here are the assignments, okay, for it. So, the compound below is 2S and S, so both of these are SS configurations, okay. Okay. Here is a little bit about Fisher projection. So this one I already explained to you. If you have straight lines, then the top and the bottom is going to the back and the horizontal ones are coming out at you. The carbon-carbon is connected by, a plane. All right, this is in the plane. It's not going back. Okay, only the top and the bottom are going to the back. And again, you can draw a molecule to see what it looks like. Okay, just like I've shown you in the video, it shows you. The 1 carbon center, if you draw it like this, okay, then this is what the representation would be. I think I went over this a little bit in one of my first lectures, but here it is, okay. So now this one is a little bit harder to visualize because we're not used to seeing 2 atoms coming out at us and 2 going to the back. So what I would say to you is just tilt it a little bit towards yourself. And when you tilt it towards yourself, then the H is going to come in the plane and the CH3 will still be at the back. And then these 2 will come out at you, which are still coming out, but now it kind of look like a tetrahedral, okay, that you're used to seeing. So that can help you. So I give you all sorts of compounds, okay, and I give you all sorts of projections also. I give you all sorts of 3D projections, so be ready for any of it. And I'm not saying you should give me any kind, but whatever you give back to me in the assignments, in the homework, make sure that you're drawing properly. You can draw a Fisher projection for me if you want to. I'm fine with that, but just make sure that if I give you a particular configuration to draw R or S, then make sure you have it, okay, that way. But I would prefer, like, if you have something like this, right? Even for your own visualization, a tetrahedral is much nicer, okay, than something like this or even like this, Fisher projections for 2 carbons, for some reason, I feel like they're a little bit easier than 1 carbon. I don't know, maybe it's my thing. I find 2 carbons a lot easier than 1 carbon Fisher projection. I don't know. I think it's my mind. Okay, for cyclic compounds, you can also have 2 chiral centers or 3, or more. So there are a few things we have to take into account when you're looking at 2 chiral centers. So first of all, if they are identical or they're different, okay, because if the groups are different, then you don't have to worry about symmetry, you don't have to worry about meso, right? So if there are different groups on the chiral centers, then no problem, okay. If you have 2 chiral carbons, then you will have the 4 stereoisomers, no problem, okay, that's going to happen. The other thing is the size of the ring, okay, and usually a 5-membered ring or a 4-membered ring is planar. So when you have planar rings, then they are going to superimpose on each other a little bit easier than a 6-membered ring. So for cyclohexane, things are a little bit different, okay, that's another thing. And then the last thing, of course, that we talk about in cyclic compounds is cis and trans, okay, and in cis and trans, you have to look and see, if those groups are in a symmetry or they are not, so that depends. And again, cis and trans depends also on if you have the same groups or not, okay, because cis and trans has to do with hydrogen. It doesn't have to do with the other group. You can have chlorine and bromine as your 2 other atoms. So, just kind of put it all together, okay, look at the ring as in a totality and not just, one thing at a time. Don't do that. Look at the whole thing. So here I've given you some examples. This one is for the 5-membered ring, and in a 5-membered ring, I've given you compounds that are cis, and then here is a trans one, okay, where you have OH going in the opposite direction. Don't mind the tilt over here. If I put it straight, then it just will not look nice, okay, as a drawn structure, but otherwise this is a cis relationship with the hydrogens on the same side, and then this is a trans, okay. But both of these compounds the mirror images are completely superimposable on each other. Okay, and again, the best thing to do is make yourself a model and see it. And I think I've done that also for you. I think I've done it for 6-membered ring, not the 5-membered. Okay, but anyway, so these will superimpose on each other, which means that they're enantiomers as well as meso. Okay, so which means even though you have chiral centers, you don't have any optical activity. There is none. Okay. Now for the other one here, in this case, you have a CH3 and an OH. So you left cis and then you still have the trans. I gave you all. Now in this case, both of these, the enantiomers here and the enantiomers here, they're going to show optical activity and there is no internal symmetry. There is nothing going on. So, these are your typical stereoisomers. So here you will have 4 isomers. And again, the relationship between this pair and this pair is that of diastereomers. The same thing here also. Okay, you still have diastereomers. It's just that you have meso also. Here in the second one where you have a CH3 and an OH, there is no meso because there is no symmetry. And then here is for the 6-membered ring. Okay, so I think, yeah, I've shown you for 6-membered ring, not the 5-membered. But if you tell me, I'll make the video for it. Okay, if you feel like, you want me to show it to you. I thought 6 was going to be a little bit more common, which it is, and that's why I made the video for it. Okay, but anyhow, let's look at the 2 rings over here. And so sometimes, you literally have to make a model and then see if it's going to be superimposable or not. Okay, because you might think, okay, here I have a 6-membered ring and I can see the symmetry, right? Really nice symmetry here with the, group coming out here, group coming out here. So this is cis and this is trans. So it seems like, okay, this might be symmetrical. Maybe this is symmetrical. I'm not quite sure because one is going in one direction, the other one is going in the other, right? So here is the chair conformation, one going up, one going down, and here both of them are going up. But when you actually make the model and you see it, okay, then you will see that they superimpose on each other. Okay, so even though you have the 2 chiral centers, they are not really chiral centers also, okay, because there is complete symmetry in the middle. I mean, there are chiral centers, I should say, they're not, okay, but actually this is really weird one, okay, because this is not going to be optically active. It's not even chiral. This kind of an internal symmetry in cyclic compounds does not even lead to chirality, so it's not a chiral center. Now in this case where you have a 1,3, this was 1,4. In 1,3, now you can have cis and you can have trans, but in this case only one of them has symmetry, the other one does not. Okay, so see, again, you're like, well, this one had symmetry, so why does this one not have symmetry? Well, draw the molecule, make the molecule out, in a model set, and then see if it superimposes or not. And that's what I've shown you, okay, in the video. So definitely watch that to see it. Don't take my word for anything, okay? So cis, there is an internal symmetry, but trans, there is none, okay? But here in trans there was, because it was completely opposite each other like this, okay, with the center of symmetry. There's a plane of symmetry and then there's a center of symmetry. There are 2 things, okay, with symmetry. It can be a little bit, I wouldn't say daunting, but molecules are weird that way, because there's so much going on. Okay, so here is a little bit of a flow chart for all the isomers that we have done. And yeah, this is the end, okay, for what we are doing as far as learning about stereoisomers is concerned. So I've given you a flow chart here and hopefully you can follow it through. So if you have some compounds, with the same molecular formula, but if they're different structures, then they're going to be constitutional isomers, okay? So if there is a rotation of single bonds, then they're just conformers, that's it. You're not breaking any bonds. With different connectivity, you can also have stereoisomers, okay? So different structures, constitutional, but different connectivity, you can have stereoisomers. Then you can have 1 chiral center, 2 chiral centers, whatnot, right? So this is your flow chart. Hopefully this helps you. And here also is another way to determine stereochemistry. If it is too busy for you or if it is too confusing, don't look at it. but otherwise you start from here and then you follow the chart through, okay, and see if you can figure out what the relationship is between each of those molecules, okay, in there. Now the chart is a little bit busy. Usually it's a lot easier when you're just looking at two molecules, you know, because if they have a different molecular formula, and that's where you start, okay, when you're given two compounds and you're asked to figure out if they are the same or not, then, you know, that's where you start from, is do they have the same molecular formula? If they don't, they're different compounds. If they're the same molecular formula but different structures, constitutional isomers, okay, are the electrons in a different place? Resonance structures, don't forget resonance also, okay. If you have two compounds but different connectivity, okay, then you can have stereoisomers but not conformers, okay. So this one is not connectivity, this should be rotation, okay. So conformers is just a little bit different. And connectivity here is, yeah, rotation. I should write here bond rotation, okay. So this is to do with, yeah, not connectivity so much. So when you have, you know, different connectivity, then you have one chiral center or two chiral centers, okay. So for one chiral center, you know, figure out the RNS. That's what I said to you before also, okay, is that, you know, instead of trying to rotate bonds, just try to figure out the RNS. That's the easiest way to know if two molecules are the same or not, okay. So in other videos, I have actually made videos for you for determining all of this. That's why I'm not including the problems in here. But I have other videos which help you to determine if the two molecules are the same or what is the relationship, okay, between the two molecules. Here are all the definitions, okay, for you. So in case you missed anything, all the explanations, definitions are given to you for all these terms that you have learned. It was a lot. It was a lot in this one. And that's it. Yeah.